Hello again. It is time to finally bring in all of our algebraic techniques to calculate some limits. So this is by far the most rigorous way to calculate a limit. The numerical methods, like setting up a chart, plugging in some numbers that are really close to the x value we're approaching, that's a tool that should not be used all the time. It can be really deceiving. There are some cases where we will actually need to use that, but for the most part, we want to try to use algebra when we can. So I'm going to go through some cases, all of the various things that we can encounter when we are calculating limits. And the first thing, we talked about this a little bit, but the first thing that we should always try is called the direct substitution property, or just direct substitution. Okay, so here's what a more formal way of direct substitution can be written as. So if we have a function f of x, and it is a polynomial. Okay, so a polynomial is just powers of x that are added or subtracted, maybe with some numbers or coefficients or constants in the front, or a rational function. A rational function is a polynomial divided by a polynomial. And the value that we are finding the limit at, we'll call it c. If that is in the domain of the function, meaning we can plug it in, then the limit is just equal to what we get when we plug in that x value. Okay, so the limit as x approaches c of f of x is just equal to what we get when we plug the number c, I know c is a letter, but it would be a number, in for x here, so it would just be f of c. Okay, so in the case where we have a polynomial or a rational function where you can basically just plug it in and get a number that makes sense out, then this property is saying that that's okay to do. I think it's saying a little more than, it looks like it's saying a little more than it is, but so this should be the first thing that you always try. This should always be the first thing to try. So I got two examples here because I think this is relatively straightforward. If we're looking at the limit as x approaches 3 of the polynomial x squared minus 2, right? Well, we have powers of x added and subtracted. I mean, this is a quadratic, but that's just a polynomial. The domain of a polynomial is all real numbers. Okay, there's nothing that you cannot plug in to a polynomial. So to find this limit, we would just say equals. And then remember, we want to put ds above the equal sign to indicate that that's what we are doing across this equal sign. We'll put the 3 in for the x, so we'll just square 3. Okay, that's 9 minus 2. And notice I'm not writing limit anymore because we're actually evaluating the limit. So we don't need that after we directly substitute. And that comes out to be 7. So that's the limit for that function. Okay, polynomials don't have any holes, they don't have any vertical asymptotes, they don't have any jumps, which is why the limit is just what you get when you plug in the x value. All right, second example, this is a rational function. Okay, we have a polynomial up top. We have a polynomial on the bottom. Now it remains to be seen if x equals 0, because that's what we're approaching, is in the domain of this function, but I think we can kind of just look and see, okay, if I plug a 0 in down here, we're not going to get a 0 on the bottom. And that is how we exclude numbers from the domain of something that has a denominator, right? So I think 0 is going to be okay. So we'll say a rational function, x equals 0, is in the domain. So in other words, we can just plug in 0. So we're going to do equals with a ds above the equal sign again. We'll do 0 squared minus 2 times 0 over 0 squared minus 3 times 0 plus 2. All right, up top we have 0 minus 0, that's just 0. In the bottom we have 0 minus 0 plus 2, so that gives us 2. Remember, 0 over a number is okay. This is actually just equal to 0. And so there is the limit for that one. Now, this is the best case scenario. It doesn't happen most of the time. So here are some cases where it doesn't work out this way. Let us consider this function here, x squared minus 2x over x squared minus 3x plus 2, same as in the previous example. But now we're looking as x approaches 2, not 0. Okay, so the first thing that we should try, always, is plugging in the 2. So the limit as x approaches 2 of x squared minus 2x over x squared minus 3x plus 2. If we were to directly substitute in, okay, this would give us 2 squared minus 2 times 2 over 2 squared minus 3 times 2 plus 2. Okay, up top we have 4 minus 4. Down bottom we have 4 minus 6 plus 2. All right, up top we have a 0. 4 minus 6 is negative 2, plus 2 is 0. So that means that x equals 2 is not in the domain of the function here. So let's note that. This means we have a hole in the graph at x equals 2. X equals 2 is not in the domain of the function, x squared minus 2x over x squared minus 3x plus 2. There's a hole. But remember, hole does not affect the limit. But in this case, there's some algebra that we can do here to simplify in one way, right? So if we factor the top and the bottom, we'll be able to remove this hole. Okay, so let's note that we can factor and cancel. Okay, so if we are going to do that, let's see, limit as x approaches 2 of x squared minus 2x over x squared minus 3x plus 2. That's just what we started with. So this is going to be equal to the limit as x approaches 2, and then we're just going to factor the top. So we'll have x times x minus 2. In the bottom, we have a quadratic. So there's a 1 in front of the x squared. So we're going to look for, let's see, two numbers that will multiply to positive 2 and add up to negative 3. I think that's x minus 2 and x minus 1. And notice here that there is a factor in common. That's where this hole is coming from. That x minus 2 up top and that x minus 2 in the bottom, that is the culprit giving us the 0 over 0. When we cancel these, we're getting a new function, right? Okay, x over x minus 1. This is a new function that's different than the one we started with. Okay, this one and this, they're different. They're only different though at x equals 2. Okay, this one you can't plug in x equals 2. This one you can. So because we're looking at the limit as x approaches 2 but never equals 2, this is okay to do. And notice that this new thing here, this is something that we can directly substitute into, and that's really nice. Okay, so we're not going to write limit anymore because we're going to actually try to evaluate that. We're going to plug in a 2 for x, and that just comes out to be 2. So this is the gist of, well, in one case, finding limits algebraically. But I do just want to really drive this point in home. It's like conceptually, it's like why we can do this. I don't want you to just memorize the procedures, although procedures are important. Equally as important as the procedures are knowing conceptually why. I think it's easier to memorize or learn stuff when you have both of those things. So just to make it really clear, okay, and I'll put like a star here. Okay, so the reason that we can do all of this is because x squared minus 2x over x squared minus 3x plus 2 and x over x minus 1. Okay, these are not the same. Right here, this one has a hole at x equals 2. This one does not have a hole at x equals 2. That's the only difference though. And because we are only looking at x approaching 2, the limits are the same. So these two, oops. Oh no, what is happening here? Just went to a completely different notebook for some reason. All right, let's find you again. Here we are. Okay. Sorry about that. So these are the same everywhere except 2, right? So these are equal. Everywhere, meaning for all x values except x equals 2. But the limit as x approaches 2 never actually considers, right? We're just approaching 2. We never actually consider x equals 2. So from the limits perspective, these two are the same. Okay, so that is the reason why that this is all okay. Okay, so here's just that kind of summarized in even a different, one more way. So something to really remember about limits and everything. A question, do holes affect the limit at a point? Well, at that point where the hole is. Do holes at a point affect the limit? And the answer is no, never. The limit doesn't see the point. That it's approaching. Okay, we just get closer and closer and closer and closer, but never actually get there. So in symbols, this idea can be summed up like this. Okay, if you have two functions, f of x and g of x, that are equal for all x values except 1, okay, so for example, this would be f of x and this would be g of x. They're equal everywhere except x equals 2. Okay, then the limit as you approach c for both of those functions are equal. So the limit as x approaches c of f of x equals the limit as x approaches c of g of x. And so what this is really saying is that it's okay and valid mathematically to kind of cancel out these things when we're finding limits. Maybe let's write that down. Okay. So what this is saying is that it's okay to factor and cancel when finding limits. And not only factoring and canceling, we'll see some other techniques too, but the idea of canceling out that hole or removing that hole. So actually, let's write that, removing the hole. Okay, so the rest of this section and the rest of this video, we're just going to kind of go through a bunch of different strategies for finding limits. I can't go through every single type of thing that you'll see, so you have to kind of, take some of this and use it in new ways sometimes. But I'm going to give you kind of a very robust list of all the different things that you'll see. So some strategies for calculating limits. Like I said, the first thing you should always try is direct substitution. So let's look at the limit as x approaches 5 of 3x minus 6 over x minus 2. Here we have a rational function. 5 is in the domain because the domain here would just be all x not equal to 2. Okay, so you can just plug in. I know we talked about this already, but just to have a nice complete list. Okay, so what, 15 minus 6 is 9, 5 minus 2 is 3, and so the limit will be 3 here. Okay, technique number 2, or strategy number 2, is one we just kind of talked about, dividing out or factoring and canceling to remove the whole. So in the first example, we have the same function as in the previous example, but now we're looking at what's going on as x approaches 2. Now 2 is not in the domain of this function, right? So we're gonna have to do a little bit of work. And when you typically have something like a polynomial over a polynomial, factoring is the way to do that. Okay, you should always keep track of what direct substitution gives. So I would recommend that you kind of do it on the side, even if you can do it in your head. Okay, we have 0 over 0, so there is indeed a whole at x equals 2. This means do more work or investigate further. Okay, so like I said, in this case, this is an example where you can try to factor. So this is going to be equal to the limit as x approaches 2. The bottom can't be factored, but we can definitely take out a 3 from the top. And here we see where the whole is coming from, right? We can now remove or fill in that whole by canceling out the x minus 2's. And what we're left with is just 3. And what is the limit as x approaches 2 of just 3? Well, that's a horizontal line like this. If you think about graphing it, the y values are just always 3 all the time, no matter what x is. And so the limit of something that's a constant like that will just be that constant. So here we have the limit of 3. Okay, let's try the next example here. We have x squared plus x minus 6 over x plus 3. And we are looking at the limit as x approaches negative 3. All right, so let's try direct substitution first. You can hear my cat in the background. She's begging to come inside. Maybe someday they will appear on camera. We'll see. All right, so plug in negative 3 into this function here. Let's see, we have 9 minus 3 minus 6. Okay, of course, over 0. 9 minus 3 is 6. 6 minus 6, that's 0 over 0. All right, do more work. There's a whole. The work to do in this case is going to be factoring, right? Because we have this polynomial up top, polynomial on the bottom. We've got a whole that we can kind of cancel out that whole with, cancel out the whole, hopefully. All right, the bottom is nice and factored. Let's see, up top, we're going to need two numbers that multiply to negative 6 and add up to positive 1. I think that those will be positive 3 and negative 2. Okay, so here we can see that we have this whole at x equals 3, negative 3, because we have these two factors that are going to cancel. Okay, make sure that you keep writing limit until we actually find it. Okay, now here is where we can actually substitute in. Okay, so we'll do direct substitution into this new function here that's the same as the original, except at x equals -3. We don't have to write limit anymore because here we're actually finding it. We'll plug in -3 and we get -5. And so there's the limit. All right, technique number 3, I'll call expanding and condensing. Okay, so here we have the limit as h approaches 0 of parentheses 3 plus h squared minus 9, and that's all over h. So there's not, I guess you could factor this. It's actually a difference of 2 squares up top, but sometimes it's not, and so I don't know, this one's just a little bit different, but sort of similar. So when we try direct substitution, even though there's an h here, don't let that bother you. We'll just plug in a 0 for h. Okay, that'll give us 3 squared up top minus 9 over, oh no, what's going on? We don't have an h here anymore, right? We have a 0, so over 0. Over 0, okay, that's 9 minus 9 over 0. Okay, so 0 over 0. Do more work. Your answer should never be 0 over 0. I'm done. That's the answer. That's never going to be right. So that always means do more work. All right, so let's see. The work to do here. Well, I would say we want to eventually work with this first because we want to eventually cancel the thing that's giving us the whole. And because h is approaching 0, the whole is going to be coming from h over h. Right, that'll be 0 over 0. So we need to kind of get at what's inside of these parentheses. So 3 plus h times 3 plus h. Maybe we can go over here on the side and figure out what that is. Right, 3 plus h squared is 3 plus h times 3 plus h. It's not 9 plus h squared. We have to have a middle term here. Okay, we'll do the first. That gives us 9. The outer gives us 3h. The inner gives us 3h. And the last gives us h squared. So we're just distributing everything. Will give us 9 plus 6h plus h squared. All right, so I'm just going to put that in instead of 3 plus h whole thing squared. All right, we've got 9 minus 9 up top, so we can just, let's just add up to 0. Okay, we have 6h plus h squared up top. That's all divided by h. We haven't yet canceled out the h yet. I think now would be a good time, almost. Remember that in order to cancel with something in the denominator, what do we have to do? I hope that in your brain something popped up along the lines of factoring out the numerator. So really make sure that you always do that. So we can take out an h from up top. That'll leave us with a 6 plus h times h in the numerator. And then that's all divided by h. And now here we can absolutely cancel these because we're multiplying by h up top and we're dividing by h in the bottom. All right, so what we have left here is a 6 plus h. And here we can finally direct substitute in. Okay, 6 plus 0 gives us 6. And so there's the value of that limit. These are really fun. I think they're really satisfying when it all works out, I guess. So that is type number 3. Strategy number 4 has to do with rationalizing. So of course, this is multiplying by the conjugate over the conjugate. And I know that this is a little tricky sometimes. So we'll go through 2 examples with this. And let's start with example number 1. The limit as x approaches 0 of the square root of x plus 1 minus 1, all divided by x. Remember, the first thing we should always try is direct substitution. So let's plug in a 0 for x. Okay, square root of 1 minus 1 over 0. Square root of 1 is 1. Okay, so we get 0 over 0. Let me go get my cat. I can show you her. Oh, come here. So this is Cordera. I call her Corey for short. Oh, my background is making her look very weird. But she's a little squirrely girl with a very fluffy tail. Very vocal too. She likes to sleep under the bed, so that's where she's going right now. All right, anyway, so we're rationalizing, right? All right, we've got 0 over 0. Of course, this means do more work. And in this case, there's no factoring to do. There's no expanding and condensing to do. The only algebraic technique that we know how to use to kind of, I don't know, get rid of this radical here is to rationalize. Okay, so let's go ahead and do that. Now our goal, because we're letting x approach 0, we're going to want to be canceling out an x over x. Right? So if we rationalize, that will kind of open up this radical here and allow us to access that x inside. So let's see, I'm just going to rewrite this. Okay, the conjugate is going to be the square root of x plus 1. Then we change that minus to a plus, and we have to do that up top and down bottom. And I'd really highly recommend that you put parentheses around everything that's got more than one term in it. Okay, so then we want to simplify this. Now when we have this situation up top, this by construction is going to get rid of any radicals. So this is a difference of two squares factored. So whenever we have something minus something else times the same first something plus the same other something else, like this, this will, when you FOIL it out, that middle term is going to fall out. So this will be x squared minus y squared. Okay, so what this will end up being, we're going to square the first thing. We square the second thing, the 1, and then we always have a minus in between. Now in the bottom, I would never ever recommend that you distribute this x into here and here, because our goal is to cancel that x. So don't ever bother distributing it out. So I would say just leave it exactly like this, x, parentheses, all of that stuff. And this is so important that I'm even going to make a note here. So I'm going to say, don't ever distribute the denominator. It's never going to help you. Factored denominator is great. That's the best kind of denominator, because then you can maybe cancel something out with the numerator. All right, so up top, when we square the square root, that's going to just give us x plus 1. Then we'll have minus order of operations. We do the 1 squared first, and then subtract, so that'll just be minus 1. Again, just going to leave that denominator already nice and factored. Oh, here's where it's getting good. The 1s are going to cancel. Then we'll have an x left up top. And finally, here's where the whole is being filled in or removed. So we can now, we've got just x times x in the numerator, times x in the denominator. So we can cancel those. And what we are left with, again, is something that's exactly the same as the thing that we started with, except we can plug a 0 into it. So that hole is filled in. So now at this point, we can directly substitute in a 0 for x. Square root of 1 is 1, so this will just be 1 over 1 plus 1. And of course, that is 1 over 2. And so there's that limit. Let's try one more of these. If you are comfortable with this, you can always skip ahead, but I think another example of this would be good. So let's look at the limit as x approaches 4 of the square root of 2 minus the square root of x minus 2 all over x minus 4. So again, I would try direct substitution first. Okay, up top we have the square root of 2 minus, that'll be the square root of 2. Of course, we have 0 on the bottom. Okay, 0 over 0. So do more work. There's a hole in the graph. Okay, the work to do here is, of course, rationalizing. So we're going to multiply by the conjugate. So I'm just going to, I know it's a little tedious to write, but that's okay. Let's rewrite this again, and then multiply by the conjugate. So that'll be times the square root of 2 plus the square root of x minus 2 over the square root of 2 plus the square root of x minus 2. Let's just stick a bunch of parentheses around everything that has more than one term. All right, so what have we got here? Well, in the numerator, we're going to square the first thing. Okay, so the square root of 2 squared, that'll give us just 2. So I'm skipping a little step here. If you need to write that out, feel free. Then it's always, always, always minus. And then we square the second thing. So that'll essentially get rid of that square root, so we'll just have x minus 2. And we're subtracting all of x minus 2. We're subtracting everything that was inside of the radical. So we need parentheses around the x minus 2. Makes a huge difference if we don't have that. Then down at the bottom, don't ever distribute this out. So, oops, I should have put parentheses around that as well. So we'll leave it as x minus 4 times parentheses radical 2 plus square root of x minus 2, close parentheses. This is looking kind of crazy, but don't ever worry about the denominator. Leave it factored because we want to cancel something out with the numerator. Okay, in this case, the whole is going to come from x minus 4. So we're going to want to cancel out an x minus 4. So it looks like we want to work with the numerator and simplifying. Okay, if we distribute the minus sign, we can make this plus minus x plus 2. So I don't have 2 plus 2, so that gives us 4, and then minus x. And then the denominator, again, we're just leaving it exactly as it is. Again, leave denominator factored. Don't use up your precious brain power to distribute that out. It's totally not helpful at all, ever. So now up top we have 4 minus x. Down bottom we have x minus 4. These can't quite cancel out. They can, but instead of getting a positive one, we get a negative one. So when we subtract things in the opposite order and we divide them, what we're going to be left with here is a negative 1 up top. I'm just going to actually move some stuff around here. Okay, so here we go. So, oops. So here what we'll have left here up top is negative 1. So what we'll have left over is going to be a negative 1 in the numerator. We'll have a radical 2 plus square root of radical x minus 2. And here we can absolutely directly substitute in because we removed that whole. So we'll do equals. Above the equal sign, we'll put direct substitution, or ds. Okay, we have negative 1 over radical 2 plus radical 4 minus 2. All right, a little bit of simplifying. That's radical 2 plus radical 2. And something plus itself is just 2 of those things. So just say 2 radical 2. Negative 1 over 2 radical 2. Now here's an example where the table, you'd be getting a decimal approximation. Like, how would you know what the values in a numerical chart we're approaching? You don't know what negative 1 over 2 radical 2 is in a decimal, and it's not, it's irrational, so it keeps on going. There's no pattern. So here is a really good example where the algebraic way is superior to the table or even a graph. All right, the fifth, we're almost there. We've got I think this is the end, 6 methods total. The fifth method is for when you have something that looks like this. A complex fraction, fractions within another fraction. So the way to do this is to just get fewer fractions. Okay, so I guess we should always try direct substitution first. So let's do that. 1/4 plus 1 over negative 4 over 4 minus 4. 1/4 plus negative 1/4, basically that's 0. Okay, so 0 over 0. All right, so we need to get a common denominator between these two fractions in order to make them a single fraction. Okay, so the LCD here is going to be, 4 times x, or 4x? So what we're going to want to do is multiply this first fraction by x over x, and the second fraction by 4 over 4. And that'll give us our common denominator. So let's see what happens when we do that. We'll get x over 4x plus 4 over 4x all over 4 plus x. Okay, let's put these together into a single fraction in the numerator. We'll have x plus 4 over 4x, then bigger divided by 4 plus x. All right, looking better. We have at least a single fraction up top instead of 2. But still, we want to simplify this further so that we can remove the whole. All right, here we have something divided by something else, and one of those somethings is a fraction. So we want to convert out of this by using keep, change, flip, or you multiply by the reciprocal of the denominator. Okay, so the denominator can be thought of as a fraction by putting it over 1. So we keep the top fraction, and we have to keep on writing limit. We'll keep the top fraction. We change this big divide to multiply, and then we flip the bottom fraction. So it'll be 1 over 4 plus x. Okay, now we have x plus 4 up top. We have 4 plus x down bottom. So if you want to be really clear, what we could do is write these as a single fraction by multiplying the numerators. X plus 4 times 1 is just x plus 4. And then the denominators. Oops. And not distributing the denominator, again, leave factored. Okay, now with addition, these are the same. So we'll just divide to give us 1. Right, you can add things in any order. So those are exactly the same, x plus 4 and 4 plus x. And so what we have here, what we're left with is 1 over 4x. And this is something that we can directly substitute into, right? We just removed the whole. So we'll have 1 over 4 times negative 4, and of course that is 1 over negative 16, or negative 1/16. And so there is that limit. All right, our last case here, or our last kind of strategy, or our last type of limit that we could see is when we might want to look at one-sided limits. So I'd say this is a not algebraic technique, and this is really the only time where you want to resort to a table. Okay, this is the only time where you don't really necessarily want to use algebra. One of those times, as you can see in this first example, is when you are looking at an absolute value function. Okay, so when you directly substitute in, you're going to get 0 over 0. But there's no algebra to do here to remove the whole. So we basically just have to make a number chart and see what's going on from either side. Okay, so in this case, and in this case, kind of only or half only, because there's one more other example, right? This is a whole or a jump, but here you want to make a chart. And see what's going on. So make a chart since absolute value is involved. Okay, so take a sec to set up this chart. Like pause the video and see if you can set up the chart here. So we're going to have x up top. We'll have absolute value of x plus 3 over x plus 3, or f of x down in the bottom, or whatever, y if you want. Okay, we'll have -3 in the middle because we're looking at a two-sided limit. And with negative numbers, it's a little hard to figure out what values that we'll choose, because on the number line, you know, negative, you go in the opposite order. So a number that's a little bit like smaller than -3 would be more negative. Okay, so to the left of it on the number line would be like -3.1. A little bit closer would be like -3.01. And a little bit closer would be -3.001. Okay, numbers that are a little bit bigger than -3, or to the right of -3 on the number line, would be like -2.9. Okay, or -2.99, or -2.999. Okay, and you can actually, if you want, you can like shade this in, right? We can't actually plug in -3, it does not exist there. There's a hole or a jump of some kind. And so when you plug these into the function, actually go do that in your calculator, see what's happening. For all the -3.1, 3.01, 3.001, I believe you get -1 across the board. And then from the other side, you get +1. So this is the case where the two one-sided limits are doing different things. Let's just move this down here so we can actually note that, right? So from the left-hand side, and practice our notation. So the limit as x approaches -3 from the left. This limit is equal to -1. But from the other side, the limit as x approaches -3 from the right, this is equal to +1. Right? And because these don't match up, what we say about the two-sided limit is that it is DNE, or does not exist. Okay? I mean, this question is asking about the two-sided limits, but sometimes you might have a question asking about from one side, and in that case, it would be either 1 or -1. But because our question is about two-sided, we have DNE. Okay, here's another case where we want to look at the one-sided limit. Okay, the limit as x approaches -2 of 1 over x plus 2. When we directly substitute in, we get 1 over -2 plus 2, and that's 1 over 0. This is actually a brand new type of limit that we haven't seen algebraically yet, but it's kind of simple. So this is not a hole. What this represents is a vertical asymptote in the graph. So a number over 0, and recall back in the video when we were looking at the graphical method, we had a function that had a vertical asymptote. Okay, so a number over 0 means we have a vertical asymptote at x equals -2. So we want to make a chart again whenever we have that kind of situation. Now at a vertical asymptote, we either go up forever, so we'll have infinity, or down forever, so we'll have -infinity. So we just want to plug in some numbers to see which situation it is. Okay, so let's go ahead and pause this and make your own chart. Okay, again, this one is two-sided, so we'll have -2 in the middle. We can't plug in -2. Some numbers that are a little close to -2, but a little smaller would be more negative, so -2.1, -2.01, and -2.001. Numbers that are a little bit bigger would be like -1.9, -1.99, and -1.999. All right, when you plug in -2.1, you can do this in your calculator. Make sure you have parentheses around the denominator. You will get -10. When you plug in -2.01, you'll get -100. And when you plug in -2.001, you'll get -1,000. So what's going on here? Okay, the limit as x approaches -2 from the left-hand side of 1 over x plus 2, what are these values doing? Are they approaching something? Not really, they're just getting more and more negative and larger, right? But negative. So there is no finite value that these are heading towards or limiting towards. So we denote this by saying that that limit from that side is -infinity. Okay, go take a look at the other side here. See what happens when you plug in -1.9. I hope you'll find that we get a 10 out. When we plug in -1.99, you will find, I hope, that we get a 100 out. And when you plug in -1.999, you will get a 1,000 out. And here, these are getting larger and larger and larger, but positively. So as we approach -2 from the right-hand side, right, we would say that this limit is positive infinity. And so graphically, they're doing this thing where I think this is exactly like what we had on our big graph that we looked at in the last video. They're doing this opposite behavior. They're not both going up or both going down. They're doing the opposite thing from either direction. So because these aren't equal to each other, we would say that the two-sided limit does not exist. Okay, so I'd like to give you a summary of all of the methods of calculating limits. And I actually have a handout for that I will just post on Blackboard. So you just see the handout. It's just like a list of what to do, and like if you get this out, then here's what you should try next. And it's just a summary of everything that we've kind of talked about, in case that's helpful to you. So this is the end of our limit journey for now. Limits will come back in the very near future in a really exciting way. I'm looking forward to sharing that with you. In the next section, section 1.6, which is our last section in this chapter, we are going to talk about something called continuity. So I will see you then, and I hope you have a wonderful day.